All right, folks. Well, let's go ahead and let's get started then. And I want to pick up with where we left off from our discussion. That is with precision and how we record precision in the precision of our measurements. We're going to talk about significant figures. Now, I just want to, before we delve into this, I just want to warn you that with significant figures, there are a set of rules. There are five rules that we're going to have to make sure we learn in order to be able to deal with significant figures, not only to be able to record them in a way that other people can read and understand our precision, but also if we were given a measurement, we can understand and we can interpret then the level of precision of each one of those measurements. Okay, so significant figures then are important, and they're absolutely important in allowing us to determine the precision of a particular measurement. Okay. All right, so let's go ahead and let's take a look at this then. And again, with these rules here that I'm going to introduce to you in just a moment, make sure you understand that these rules, just like with rules in math or in grammar, I pointed this out to you before, you just have to learn them. And you can choose either to memorize them or you can choose to learn them by practice. And I always suggest that you learn by practice. It's just that it ingrains those rules into your head a little bit more than trying to memorize them, okay? All right, so with that said then, when we talk about significant figures, what we're doing is that we're counting digits, okay? And when we record these, when we are responsible for recording significant figures, the precision, remember, is going to be based upon the instrument that we use, the level of calibration that we have. And typically when we record the significant figures and your POGIL activity, will give you an opportunity to see this, okay? When you record the significant figures, it's going to be the numbers of digits that are given to us by the particular measuring device plus one estimated digit as well. Okay, so that's what's going to be significant. That's what we indicate as being significant. Okay, and so we got to write down all those digits. Okay, so we always want to make sure when we are recording, when we write down these our measurements, that we follow this one very simple rule, and that is, again, we record down all the digits that's given to us by that particular measuring device plus one extra estimated digit. Okay. All right. So with that said, then that's if we are recording these significant figures down. Okay. However, if we are given a measurement, okay, how would we know then the level of precision of that particular given measurement? Well, it comes down to a set of rules that we're going to use, okay, and the set of rules that we as the scientific community have agreed upon, okay. And so, like I pointed out to you, these rules are fairly arbitrary, just like most rules are, okay. But we have to learn them, and if we learn them, then we'll be able to use them and instruct then the level of precision for these particular measurements. Okay. All right, so there are five rules that you have to learn, okay? And so with these five rules here, let's go ahead and go through each one of the five rules, and then what we're going to do is we're going to apply them, okay, and then practice them. Okay? All right, so let's take a look at the first rule. First rule then basically tells us then that every non-zero digit is significant. That means whenever you see a non-zero digit that's written down, it's meant to be counted as being significant as part of the precision of that particular measurement. Okay, so if you take a look at the three measurements that are given to you here, so you're given three measurements here at 24.7 meters, 0.0743 meters, and 714 meters. Okay, so let's go ahead and let's take a look at this here. What you'll notice then is that 2, 4, and 7. A non-zero digit is simply a digit that's not zero. So 2 is not 0, 4 is not 0, 7 is not 0. So all three of these digits then will be significant. And so we count that as three significant figures. Okay, so there would be three significant figures in this particular number. Let's take a look at the second measurement here. The number then is 0.743. Okay, we have three non-zero digits. 0 here is obviously 0. We have three non-zero digits here. And so this is also three significant. And I abbreviate significant figures with the SF. Okay. And then finally, the last measurement here, the number is 714. 7, 1, and 4 are non-zero digits. And so we have three significant figures here as well. Okay, so for each one of these numbers here, then, for each one of these numbers, okay, in each measurements, we will have three significant figures. Okay. All right, that's rule number one. Okay, let's go ahead then and let's take a look at rule number two. Now, the first rule, so of the five rules that deals with significant figures, the first rule then deals with non-zero digits. Okay? The remaining rules then deals with the zeros. So I would suggest then that what you do is you focus in on the zeros, and we differentiate between the zeros. The non-zero digits, that's easy to identify. Okay, you have to be able to identify the zeros and what to deal with them. Okay, all right. So the first rule that deals with zero, which happens to be rule number 2 here. Okay, the first rule that deals with the zeros tells us then that zeros that are sandwiched between two non-zero digits will be counted as significant. We count them. Okay, so what does that mean? Let's take a look at the first number here. Let's take a look at the first number here, and let's take a look at it. So the 7 and the 3, non-zero digits, those count. So the 7 and the 3, let's go ahead and write that down. Okay, so the 7 and the 3, those are significant. They have to be according to rule number 1. We have then 2 zeros right here. Okay, the 2 zeros are sandwiched between, meaning that they sit between the 2 non-zero digits. So these 2 zeros here sit between the 7 and the 3, and so therefore, according to rule number 2 here, those zeros count, and so therefore we have 4 significant figures in this particular number. Okay. All right, let's go ahead and take a look at the second number here. Okay, so we have 40.79. So the measurement is 40.79 meters. The number then is 40.79. We have a 4, a 7, and a 9. Those are non-zero digits. We expect those to count. Okay, here is a 0. This 0 sits between the 4 and the 7. Okay, it's a 0 that sits between 2 non-zero digits, and so therefore, for this particular number, we have a total of 4 significant figures as well. All right. Let's take a look at the last measurement here. Okay, so the number for this measurement is 1.503. The 1, the 5, and the 3, they count. Okay, and this 0 here is a 0 that sits between the 5 and the 3. It is a 0 that appears between 2 non-zero digits. So it also is significant. So we have then 4 significant figures in that number as well. So in all 3 of these measurements, we have 4 significant figures. Okay. All right, that's rule number 2. All right, rule number 3 then deals, let's go and take a look at rule number 3. Okay. Rule number 3 then deals with zeros that what I refer to as the leading zeros. These are the zeros that are the leftmost zeros. These are the zeros that come before the first non-zero digit. Okay, so when we talk about the leftmost zeros, okay, so let's go and take a look at this here. Okay, what these leftmost zeros mean then, the zeros that are furthest to the left. Okay, so let's take a look at each one of these measurements here, and let's take a look at this and what we have. Okay, so with that said, then if you take a look at here, okay, we have the 7 and the 1. Those are non-zero digits. We expect those to count. Okay, here are some zeros right here. Okay, these zeros here are not in between. They're not sandwiched in between the 7 and the 1. So rule number 2 does not apply to these zeros. Okay. However, these zeros are leftmost zeros. These are the furthest to the left, but they come before the first non-zero digit. So they precede the first non-zero digit. So these are the leftmost zeros. They do not count. They are not significant. So therefore, this number then has, this number then will have 2 significant figures. Okay. All right. Let's go ahead and let's take a look at the second measurement. The second measurement here, the 4 and the 2 non-zero digits. We expect those to count. We have this 0 here. It precedes the first non-zero digit. It is a leftmost 0. So again, according to rule number 3, that 0 does not count. It is not significant. So therefore, we also have 2 significant figures in the second measurement as well. Okay. All right. And so let's take a look at the third measurement here. We have 0.00000000099 meters. The 2 9s are significant. They're non-zero digits. Okay. All of these zeros here are leftmost zeros. They are leading zeros. They precede this first 9 here. They're not significant. And so therefore we don't count them. And so in this last measurement as well, we have 2 significant figures. And so in all 3 of these measurements here, we have 2 significant figures. Okay? And that's according to rule number 3. All right, let's continue on then. Let's continue on with all these rules, and then we're going to practice this. Okay. All right, rule number 4. Let's go ahead and take a look at rule number 4. Rule number 4 then, and rule number 5. Rule number 4 and 5 deals with zeros that are the zeros to the right. These are the rightmost zeros. Okay, so the zeros furthest to the right, when there is a decimal point present, and I want to make sure I clearly I make this as clear to you as possible. Okay, so whenever we have a decimal point, and you're gonna look for that decimal point. Okay, and so if a decimal point is clearly written in there, not implied, it's not an implied decimal point, but it is a clearly written decimal point. If there's any zeros to the right of that decimal point, they will count. They will be significant. Okay, let's take a look at the three examples here. Okay, so 43.00 meters. Okay, the 4 and the 3 obviously count. Okay, they are non-zero digits. Okay, we have zeros here. These zeros are not to the left. Okay, they are not leftmost zeros. They are to the right. They're to the right. And if you see here, there's your decimal point. The decimal point is clearly written in there, and so therefore those zeros do count. So therefore, you have 4 significant figures in this particular number here. Okay. All right, let's go ahead and let's take a look at the second number here. Okay, let's go ahead and count this. We have the 2 1s. They're non-zero digits, so they do count. Okay, we have 2 zeros here. Okay, we have a 0 that is between 2 non-zero digits, and we have the 0 at the furthest right. Okay, all right. We know that rule number 2 tells us that any 0 between 2 non-zero digits that it counts. So therefore, this 0 counts. So what about this 0 here? Well, rule number 4 here tells us then that if a decimal point is clearly written, there it is, the zeros furthest to the right, they do count. Okay, so therefore that 0 does count. So therefore this number here has also 4 significant figures. Okay, all right. Let's take a look at the last measurement. Okay, we have then the 9 non-zero digit that counts. Okay, and then we have these 3 zeros right there. Okay, those 3 zeros are the they're zeros furthest to the right. Okay, and so is there a decimal point clearly written in there? Yes, it is. Yes, it is. So there's your decimal point clearly written in. So those 3 zeros do also count. They are significant, and so therefore that number also has 4 significant figures. Okay? So in each one of these numbers, then each one of these measurements, I'm sorry, each number has 4 significant figures. Okay? So that's rule number 4. Okay? Let's go ahead then. Let's take a look at the last rule here, and let's go through this. Okay? The last rule then deals with zeros furthest to the right. Again, the rightmost zeros, and so we're dealing with the rightmost 0 again. Okay, let me go write this down. So again, we're dealing with the rightmost 0. Okay, so this time though, if the decimal point is understood, if an understood decimal point, which means it simply means then a decimal point that is not clearly written in there. Okay, if that is the case, then the rightmost zeros do not count. They are not significant. Okay, they are not significant. They basically serve as these placeholders if you want to think about it. Okay. All right, so let's take a look at our first measurement here. We have 300 meters. Okay, the 3 obviously counts. It's a non-zero digit, but then we have 2 zeros to the right of that 3. However, the decimal point is understood to be right here. It's not clearly written. It's understood to be there, and so therefore these zeros then do not count. So therefore, we only have 1 significant figure for that particular number. Okay. Okay, very good. Let's go ahead and let's take a look at the second measurement then. We have 7,000 meters. 7 obviously counts. It's a non-zero digit. Okay. These 3 zeros here, they are to the right. They are rightmost zeros. However, there's no decimal point written in there. That decimal point is understood to be right here, but it's not clearly written. So therefore, those 3 zeros do not count. This number here also has only 1 significant figure. Okay, so both of these measurements here then only have 1 significant figure, even though these are the trailing zeros. I call these trailing zeros, the rightmost zeros. Even though they are there, you only have 1 significant figure. Why? Because there's some ambiguity in this. That doesn't mean that those zeros are not significant. We just don't know because whether the precision of the rulers that were used here is to the ones place or to the hundreds in the case of the first measurement or the thousands in the case of the second measurement. We just don't know. The person who took these measurements did not record that decimal point, so we don't know the level of precision of these particular rulers here. And so therefore, we just have to go with what we think it is, and so it's going to be 1 significant figure in each one of these. Okay. All right. Those are the 5 rules that deal with the digits. Okay, there is one last rule that I want to make sure that you point out to you, and that is the last rule here for significant figures deals with what we call counted quantities or defined values. Okay. Counted quantities simply are numbers that we obtain from a count. We don't measure it. There is no, we're not taking a ruler to measure it. These are not measured values. These are counted quantities. There's no tool that we use to count these values. Okay? So they are numbers. They are numbers, but because we count them, the level of precision is infinite. Why? Because you get an exact number. And so essentially what this last rule deals with then is what this last rule deals with then are exact numbers. That is, there is no ambiguity. The level of precision is highly precise, okay? Because we don't need to estimate. When we count out the number of students in our classroom, okay, there are 12 of us. It's not 12 and a half, okay? It's not 11.5. When we count out the number of students, okay, there's exactly 12. There is no estimating. There is no guessing in that. It's an exact number, okay? So whenever we have an exact number, the level of precision we say then is infinitely high. So therefore we say then that we have an unlimited number of significant figures whenever we have a counted number, a number that we obtain by counting. The second situation where we have an exact number is when we have what's called defined quantities. Now, these defined quantities will come into play a lot more when we deal with conversions. With these counted quantities, then, make sure you understand this. These counted quantities, these defined values are equivalences. We're saying then that two measured values are exactly equal to one another. For example, we know then, and we have accepted as a fact, because everyone uses it, that there are 60 seconds in 1 minute. It's not 59.9 seconds in 1 minute. It's not 61.5 seconds in 1 minute. It's exactly 60 seconds in 1 minute. Now, obviously, that's a very arbitrary association, but because we have accepted that as an equivalence, we say then that those two measured time values are exactly equal to one another. And so those two numbers are exact. And like I had pointed out to you, whenever you have an exact number, okay, the level of precision is infinitely high. And so therefore then we say that we have an unlimited number of significant figures. And that's only going to be true for these two conditions here. Okay, so make sure you keep that in mind as we go through this. Okay. All right, very good. Let's go ahead and let's practice this. Okay. Let's go ahead and take a look at these seven numbers here, and let's work through this. Okay. All right, so for the first number here, we have 456. The measurement is 456 milliliters. Okay, let's go ahead then and let's indicate the number of significant figures. Okay, all right, 4, 5, and 6, all non-zero digits. According to rule number 1, that means that all of them are significant. We have then 3 significant figures in that particular number. Okay, all right, let's take a look at the second number here. Okay, the second number here is 70.4. The measurement is 70.4 meters. Okay, but the number is 70.4. The 7 and the 4, they count. They are significant because they are non-zero digits. Okay, the 0 here does count. It is significant. Why? Because according to rule number 2, you have then a 0 in between 2 non-zero digits. That's also significant. Okay, so you have 3 significant figures here as well. Now, mind you, I'm referring to the rule here. I'm saying it's rule number 1, rule number 2. That's because I've done it long enough where I've remembered these rules. What I would suggest you do is that if you can memorize the rules, good for you. But make sure you can apply them. Okay, make sure you can apply them. And so practice this. And as you practice this more, folks, I guarantee you it's going to get ingrained inside your mind. Okay, all right. Let's go ahead then and let's take a look at the third measurement. Okay, the number here is 444,000. Okay, and so with that said, then all of these here, those 3 4s, they count. They are significant because they're non-zero digits. What about these 3 zeros right here? Well, first of all, identify what type of zeros they are. They're not in between 2 non-zero digits. They're not the leftmost zeros. These are the rightmost zeros. Okay, and then once you've identified that, you need to make sure you ask yourself, is there a decimal point that is clearly stated in here, or clearly written, or is it understood? Well, in this number here, the decimal point is not written in. It is understood to be there. Okay, it's understood to be right here, just to the right of this 0 here. And remember, according to rule number 4, okay, rule number 4, that 0 then, I'm sorry, rule number 5, that 0 does not count. These zeros do not count because it's ambiguous. Okay, and so therefore, this number then also has 3 significant figures. Okay. All right, let's take a look at the fourth number here. Okay, We have then 0.00406. The 4 and the 6 obviously count according to rule number 1, non-zero digits. This 0 does count. It is significant because it's in between two non-zero digits. What about these 3 zeros right here? Okay, those 3 zeros are leftmost zeros. Okay, and remember, leftmost zeros never count, regardless of the decimal point. They never count, and so therefore this number also has 3 significant figures. Okay? All right, let's continue on. 0.90 liters. Okay, all right. The 9 obviously counts. The non-zero digit. Okay, we have 2 different zeros here. We have a leftmost 0. We have a rightmost 0. Okay. The leftmost zeros, remember, they never count, so we can get that out of the way right now. But what about this 0 here? Okay, remember, these 3 zeros at the top here, they did not count. They're furthest to the right, but the reason why they did not count, they did not count because there was no decimal point clearly stated here. Here, you clearly have the decimal point written right there. There's your decimal point. Okay, so therefore, that 0 does count. It is significant. Therefore, you have 2 significant figures there as well. Okay. All right, 2 significant figures there. Okay, let's go ahead and take a look at the last 2 examples here. Okay? 56 eggs in a basket. The number here is 56. Okay, the number here is 56. But do understand the difference between this number here and all the numbers, the 5 numbers that preceded it. These numbers, this 56 here indicates a number that is counted. We've counted out 56 eggs. The other way that you can imagine this, or the other way you can see this then, is that this is not a measured value. We've counted it out. All of these are measured. This is a volume measure. This is a length. This is a mass. So whenever you have a number that you obtain by measuring, we have to deal with the significant figures. We got to deal with the significant figures here. However, if we have a number that is not measured, but it's counted, like it is here, it is an exact number. When we counted out 56 eggs in a basket, there's no estimating involved in there. We just counted it out. And so therefore, according to rule number 6, this number here, this number, 56, has an unlimited number. It's an infinite number of significant figures. It is infinitely precise. That's how we want to think about it. Okay? All right, let's take a look at the last example. We have 2 numbers here. We have 12 and we have 1. How are we supposed to deal with this? What's the level of precision for each one of those numbers? Well, understand this. This is a defined value. We have accepted the fact that when we refer to the word dozen, whenever we have 1 dozen, that is exactly equal to 12. 12 or whatever we have. Here we have eggs. Okay? So whenever we have 12 eggs, that is exactly equal to 1 dozen eggs. When we have 12 donuts, that's 1 dozen donuts. So these 2 numbers here are exact numbers. It's not 13 eggs for 1 dozen. Okay, I'm sorry, that's a baker's dozen, but that doesn't count. Okay. But whenever you have a dozen, we know then that the number 12 is associated with it. Not 11 and a half, not 12.1, but 12. So these 2 numbers are exact numbers, which means then we have an infinite number of significant figures. So this is a counted quantity. So whenever you have a counted quantity, 56, or you have a defined set of quantities here, 1 egg, 12 eggs, 12 in a dozen. Okay, whenever you have these 2 conditions here, you always have an infinite number of significant figures. Okay? All right, very good. Let me go ahead then. I'm going to ask you, let's go ahead and let's do number 10 in your problem set. Let's go and work out number 10 in your problem set. Take a couple minutes to work this out. Okay, and then we'll go over. Okay, so go ahead, work this out. Take a couple minutes, and then we'll work this out. We'll do this together. Okay. All right, let's take a look at this here. Okay. All right, first number, we have 11. Okay, the number is 11, but look at what we have in terms of the units. This is soccer players. Essentially what what we're being told there is that we have counted out 11 soccer players. Okay, so if this is a counted quantity, the number of significant figures here, infinite. Okay, so make sure you have that written down. Okay. All right, let's take a look at the next number here, 0.070020 meters. This is a measured value. Let's take a look at this number here. Okay. All right, so let's indicate obviously the 7 and the 2 are significant, okay, non-zero digits. Okay. Let's take a look at these 2 zeros here. These 2 zeros are in between the 7 and the 2. They are significant. Okay, so we have 4 significant figures so far. Now we have to deal with these zeros at the front. These are the leftmost zeros. Leftmost zeros never count, so we don't count those. And then finally, we have this 0 here, which is furthest to the rightmost 0. And so we have to ask ourselves, is there a decimal point clearly written there? And there it is. There's your decimal point right there. So therefore, that 0 does count. So we have 1, 2, 3, 4, 5 significant figures in this particular number. Okay. All right, let's take a look at the third number here, 10,800. Okay, the 1 and the 8 obviously count. Okay, the 0 here is sandwiched. It is in between the 1 and the 8, in between two non-zero digits, so it counts. Okay, and what about these two zeros here? These are furthest to the right. They are furthest to the right, but is there a decimal point that is clearly indicated in this number? And the answer is no. So therefore, those zeros do not count. We have then 3 significant figures in this number. Okay. All right, let's take a look at the last number here. Okay, 5.00. Okay, the 5 obviously counts. These two zeros here are furthest to the right. They are rightmost zeros. And so they count only if the decimal point is clearly written there. And there it is. There's our decimal point. So those two zeros do count. We have then 3 significant figures here as well. Okay. All right, very good. Let's go ahead. Let's do one more. Okay, let me go ahead and ask you to do number 4 here in your problem set. Take about a couple minutes to work out number 4 here in your problem set, and then we'll work that out together. Okay, go ahead and get that done. Okay, let's go ahead and let's take a look at each one of these. I'm going to work these out for you real quickly. Okay, let's take a look at the first one. Okay, so again, 1, 2, 3 non-zero digits. Those 3 digits are non-zero digits, so therefore we have 3 significant figures in this number. Okay. Second measurement, 9 and 8, they count. They're non-zero digits. These 3 zeros here are rightmost zeros, what I refer to as trailing zeros. I get into the habit of calling them that, so make sure you understand when I say trailing zeros, I'm referring to zeros that are furthest to the right. Okay. All right, do they count? Yes, they do. There's a decimal point right there, so we have then 5 significant figures in this particular number. Let's go ahead and take a look at the next example. Okay, the next problem, we have 0.0787080. Okay, 7 and the 8, obviously they are significant, non-zero digits. Okay, the 0 here, it's between the 7 and 8, it counts. Okay? The leftmost zeros, these leading zeros, they never count. Okay, so even with the decimal point there, don't confuse the decimal point. The decimal point only applies to trailing zeros. Zeros furthest to right, and so therefore, since you have the decimal point here, this zero is furthest to right, it counts. And therefore, we have 4 significant figures here as 4 significant figures here. Okay, all right. Let's continue on. 40,506. The 4, the 5, and the 6, they all count. They are non-zero digits. The 2 zeros here are in between 2 non-zero digits. Okay, so this 0 here is between the 4 and the 5. This 0 here is between the 5 and the 6. So therefore, all those zeros do count. Therefore, we have then 5 significant figures here as well. Okay. All right. 22 meter sticks. Okay. If you notice here, and again, what you want to do is make sure you key in on this. Okay. What you want to notice here then is that the unit there, this particular description here is not of a particular unit. It's not a unit. It's just it tells us an object that is being counted. Okay. So therefore, this is a counted quantity. So we have then not 2 significant figures, but we have an infinite number of significant figures in this particular number here. Okay. All right, let's look at the last measurement here, 98,000 meters. Okay, so the 9 and the 8 obviously counts. These 3 zeros are at the end. These are the trailing zeros, furthest to the right. Okay. Do they count? Well, they don't count because remember, there's no decimal point clearly written in this particular problem. And so therefore, then you have 2 significant figures that are present in this particular problem here. Okay. All right, very good. Let's go ahead then and let's continue on. Okay, and I want to quickly, with the time that I have here, little time that I have left here, I want to go ahead and I want to talk about the significant figures when we talk about calculations. Okay. Now, actually, let me do this. I'm going to pause right here. Okay, and then what we'll do is in the next lecture, I'm going to talk about how we deal with significant figures in calculations. I want to practice this a little bit more when we meet, okay, and then give you a chance to watch the video and practice this, and then we'll continue on with significant figures when we deal with the calculations. Okay, so on the next Edpuzzle video, on the next lecture, okay, we'll talk about the significant figures in calculations. Okay, all right, very good, folks.